Yeah. Okay. We want to talk about TLS and what's broken with TLS and what is this thing about Beast and crime and Lucky 13 and especially Heartbleed. Yeah, a quick introduction of myself. I'm a journalist, a freelance writer, and I often write about crypto topics. I often write for Golem, which is a German IT magazine, most of you probably know. And I also run some web hosting, a small company that does web hosting, and so I also am interested how to configure my servers that the encryption is secure, somewhat secure, and that the browser still can access it, and yeah. Yeah. Why do we talk about TLS? It's quite obvious. TLS is the most important crypto protocol at all. Probably everyone who uses the internet uses TLS all the time for emails, for banking, for just everything. And we have a lot of problems with TLS in different layers. We have certificate authorities, which is a big problem. We have software that we just saw that's maybe not so good. We have some problems with the cryptography itself because it's often outdated cryptography, stuff that's not as secure as we would like it. And we have protocols that are in many aspects not as we would like them. And we had lots of vulnerabilities with funny names in the last years, especially Beast, Crime, Lucky 13 and Heartbleed, which was the latest. I didn't know about Heartbleed when I submitted this talk, obviously. It was sometime in January. So I'm kind of lucky because now there's a lot of interest in the topic. But also I had to completely change my talk because after Heartbleed I thought I have to get a much broader view on the whole topic of TLS, because originally I mostly wanted to talk about the crypto algorithms, and I think the problem is bigger than that. So a quick history of TLS. It was called SSL, and many still call it SSL. I'm saying TLS because that's the correct name that's in the standards. And if you use it today, it's usually TLS. The first version was only an internal development at Netscape. The second version was the first public version in Netscape Navigator in 1994. It had severe security problems, really like problems that you could break the encryption. And so quickly a new version was designed, which is SSL version 3, which is also quite old today. It's almost 20 years, but still it's used a lot. You can try, if you disable it in your browser, you will find some web pages that don't work. And then in 1999, we had the first standard TLS, which was then developed by the IETF. This is the Internet Engineering Task Force, which does all the standards like HTTP or SMTP. Everything basically that runs the internet is a standard by the IETF. The first problem had some security problems with CBC, but nobody cared, and they are still using it today mostly. Then there was TLS 1.1, which fixed half of the CBC problems. The other half is still there. And then we had TLS 1.2, which introduced authenticated encryption. I will explain later what that is. And GCM mode, which is called counter mode for encryption, and SHA-2. So, and yeah. I will explain later what problems there are and how they fixed it. The other problems are still there, but there are some workarounds. Yes, they were known. I will show you later that they were known. I will explain it in detail. Yeah, and the basic idea how TLS works is that at first we have X509, which is the certificate standard, and we have certificate authorities that sign a host certificate for HTTPS or any other kind of server. And this certificate contains a public key, and this is used to establish a connection with TLS itself. So we have two protocols involved. It's X509 and TLS. And I think we have four layers where we have problems. That's software, that's certificate authorities, that's X509, and it's TLS itself. So software. Heartbleed is only a software problem. It's just a memory read error. So it's, some cryptographers might say it's just boring, has nothing to do with cryptography. I read a blog from a cryptographer who said exactly this. And I think this is kind of the problem, that crypto people sometimes don't see the big picture, because you implement crypto in software, so it is a problem. Our SSL software is really scary quality. I don't know who knows the webpage OpenSSL Valhalla Rampage. It's been set up a few days ago. The OpenBSD people are currently trying to fork OpenSSL and remove everything that's strange, and it's a lot. Read it, it's funny and scary.
Will there be remainders?
Not sure yet.
I don't know that.
No untouched files.
Well, really, today they removed some Cray code. I don't know. Yeah.
Well, Cray has 64-bit integer type, so a simple cint is 64-bit on Cray CPUs, and this is incompatible with OpenSSL crapware because they refuse to use stdint for fixed size integers. Instead, they have their own evil macros to guess the right integer type for each size in bits.
Yeah. I don't really know what the Cray code was about, but it's all kind of that weird stuff that they are currently removing. And I hope this thing will become usable also for other systems like Linux, because I don't use OpenBSD and I think I want to continue using Linux. So but I think I would like to use this improved OpenSSL. I also hope that the OpenSSL project will incorporate some of the changes, at least the obvious ones. But I also want to make this pretty clear. You shouldn't blame OpenSSL too much, because the others just aren't better.
Sorry, but there are. OpenSSL is a sorry piece of shit.
Have you read NSS code?
It's always possible to get a little bit worse.
I mean, NSS is used.
They use copy and paste for some.
Yeah.
Come on.
Yeah. I wrote some code in NSS, and it's also terrible.
I found limitations in every major crypto lib.
Yeah. Yeah, and I mean, that's kind of a discussion that was going on the last days, that I really also don't think it makes sense to blame the people, because I mean, this is a project that is run by mostly volunteers, and I think given the circumstances, they probably make quite a good job. Yeah. But basically, we have obviously problems with the software. Now, one of the problems I think, is feature bloat. If we look at this Heartbeat extension that created all this Heartbleed bug, nobody uses it. I asked a lot of people, what's this for and why did we create it? And a lot of people answered me what you could do with it, but nobody said, like, here's a piece of software that's doing something useful with it. So it's basically just an extension that was made. It was made in a PhD thesis. So, I mean, you know, if you do science and you have to write your thesis, you will probably write something that you think is useful, and you will probably try to explain that it's useful. But maybe we should ask the question if we should put this into standards and into software and then enable it on all web servers. I'm not sure if this is the best idea. I think we should also look what other features and extensions there are in TLS, and ask ourselves, is this needed or is just crap that should be removed? And do we need really the algorithms like Ghost, DSA, Seed, IDEA, brainpool curves, or Camellia? Ghost is, if you don't know that, a standard from the Soviet Union. It's no joke. There's just a draft for TLS, but OpenSSL still has support for it, but it's disabled by default, so I hope it won't matter. But what you have to think here is all these algorithms, the code is there, they can be used, but usually they aren't used. So you can expect probably not so many people have a look at it. We have a lot of discussions after the Heartbleed bug. Many eyes principle, and is open source more secure? And I think here's a problem, because if we have parts of the code that are rarely used and rarely looked at, then security bugs can hide there. TLS also supports completely insecure algorithms, the standard, like DES or RC2 with 40 bits. It's yeah, null ciphers that do nothing. Yeah, but for example, Conqueror supports all of these. Yeah. So I think trimming down the features, and I wrote this on the TLS mailing list, and I think I got some support, and I will probably try to write a draft for an RFC that we deprecate a lot of algorithms that are rarely used and that are insecure, and maybe this improves things a bit. Then we have C code. We know that it's difficult to write secure C code. I probably can't write secure C code. I can write C, but it's probably not secure if I do it. And people who know about this stuff say there are very few people who are able to write C without having buffer overflows or memory read errors. But I think this is a difficult question, because then some people come and say, okay, just use Java or Dylan or OCaml, but it's not so trivial to find a better programming language. We need to think, what do we need for a programming language? And I think it shouldn't be too exotic, because if we write a SSL implementation in Haskell or Dylan or whatever, we have the problem it's difficult to get a community around it. I saw this with other software projects. For example, I'm using eJabberD, which is written in Erlang. I have no idea how to write Erlang code, and if I report bugs, I can only hope someone will fix them, because I cannot do it myself, and probably a lot of people have no idea to write Erlang. So I think we need a programming language where a lot of people know at least a bit about it. Then it shouldn't be too much overhead, because the reason OpenSSL is so successful is partly because it runs on so many different devices. For example, you cannot run Java on an OpenWrt router or on some other embedded device. And so I don't think anything that's too bloated, either the code or the runtime environment, that, yeah. So I think, for example, Java is definitely not the answer. And by the way, we need something where we can write constant time implementations, because timing attacks are a big problem in crypto. And for example, just a few days ago, there was a bug in the SSL code of Java, which was that there was an exception thrown in some code, and this caused a timing issue. So yeah. And then there's the idea, some people say maybe we can make C but secure. OpenBSD has an malloc implementation that checks the memory boundaries. So it could have stopped Heartbleed. The thing is, OpenSSL has its own malloc implementation, so it didn't work. Then there's a project which I find very interesting. It's called Softbound CETS. There was a talk on the last Congress, which is very interesting. I tried to build OpenSSL in it, but it's just too alpha. It doesn't support a lot of things. But basically the idea is make C, but make everything memory safe, so that memory violations cannot happen. If if this would work, I think maybe this is a very good solution for this problem. Yeah. Then we have certificate authorities. I think this is probably the biggest issue from all of them. The main problem is your browser has like some 100 certificate authorities and it trusts them, so you trust them, although you have no idea what strange organizations they are, and some are known to sell equipment to do man-in-the-middle attacks, so you can expect maybe they will also sell the certificates for it. And you automatically trust them all, and also all the sub-CAs, and you don't know what sub-CAs there are. Every CA can sign a sub-certificate authority that can sign everything, and your browser will accept it. And the weird thing is, it doesn't matter if you trust your own CA for your website, because, for example, I use certificates from Start SSL, and sometimes people tell me there are some dubious company. I don't think that, but it just doesn't matter because every CA can man-in-the-middle my web pages, no matter what kind of certificate I use. Yeah. Then in 2011, we had a big CA disaster. Several certificate authorities issued fake, wrong certificates. The EFF SSL Observatory did something very interesting. They just scanned all IPv4 addresses and took the certificate and looked what's there. And they found all kinds of weird things, like extended validation certificates with 512 bits, which is completely insecure, and certificates with
ECDSA or ASA?
RSA. Yeah. Certificates that were a CA and not a CA at the same time, and valid certificates and all kinds of stuff, yeah, and localhost certificates and certificates for mail, and yeah. DigiNotar also issued certificates for Google and some others which were not requested by Google. They were the only CA where this had any consequences. They got bankrupt and they were removed from the browsers. Komodo also issued like I think 200 fake certificates for Google, Yahoo, Skype, Mozilla, and nothing happened to them because Komodo is really too big to fail. Mozilla cannot remove the Komodo certificate because then a third of the internet wouldn't work anymore. That doesn't work. So basically, a CA, if it's big enough, it can do all kinds of crap because you cannot remove it from the browser. Yeah, big problem. Then we have revocation. Revocation is very interesting. We had it just with the Heartbleed bug. The idea is if a certificate, we know that it's been hacked, then we can like sign, the certificate authority knows that and it has a list which certificates are invalid. Originally they had lists of certificates. It's easy to see that this doesn't scale. If there are a lot of revoked certificates, then the list is too big. Then we had OCSP. The idea is the browser asks the certificate authority, is this cert still valid? The problem is, first problem is privacy. The certificate authority will know which web pages you serve. Second problem is it's implemented insecure because what the browsers do is if the certificate authority doesn't answer, the certificate is considered valid. Because these OCSP servers are just not reliable. And there's another problem if you go to, for example, train station and you go to the, you get some kind of login page. And it's usually SSL secured because you enter your password. But at that point, you don't have internet. So the browser cannot check if the certificate is valid. Yeah, that's another problem. So, and Chrome did something very simple. They disabled it because they said it doesn't work, so we can also disable it. And bottom line is, yeah, after Heartbleed, a lot of people said revoke your certificates, but it doesn't work, so it doesn't matter. Yeah, another thing with revocation, Start SSL charges money for revocation, so you get the certificate for free, but when you want to revoke it, you have to pay. And this is not good because it gives you an incentive to do the wrong thing. If your certificate is hacked, then you should replace it and revoke the old one, but you have to pay for it, so you don't like to replace it. So you may say, okay, then I just go on with the old certificate. And you could say, okay, it doesn't matter because revocation doesn't work anyway. But this also shows a more general problem that the whole system is like you have to pay for a certificate. And so it is, if you want more security, you have to pay. And if you think about it, it should be the other way around. It should be if you have less security, it should be bad for you. And if you have more security, it should be good for you. There are a number of ideas how to fix this, but they are all quite complicated. Convergence is quite an old idea. It's just basically saying we look at a certificate from different points in the internet, but there still man in the middle is possible if the attacker is near the server. Then sovereign keys is a very advanced idea, but it's just an idea. There's no protocol specification. It's from the EFF, which uses something, it's a bit similar to Bitcoin. It uses some kind of eternal log file where you can only append information. There was a talk on the Congress a few years ago. It's quite interesting, but it's really, you think, yeah, might work, but it's really difficult to do. TAC is a bit similar. It's kind of a certificate pinning where you can say, this is my certificate, and dear browser, please remember if it changes, then only if I allowed this change or someone who I say is allowed to do this change. And there's a similar draft from Google, which is HTTP key pinning, which is only for HTTP. I don't know why. It's because we need it for all TLS services. And another project from Google is certificate transparency, where the idea is that if someone uses a certificate and the browser sees a certificate nobody has seen before, the browser will tell someone else. And there are also like some append-only logs. I think this is quite an interesting idea. It will not stop attacks with certificates, but it will make them transparent, so you cannot hide your attack. And the good thing is it's from Google, so maybe it has chances to be realized, because really having a good idea is one thing, but getting it into the real world internet is another thing. Yeah. Okay, then we have the protocol itself for certificates. It's X509. X509 is an extremely complicated protocol. I think it's from the 80s, from the ITU. It was invented long before the internet and before domain names, and it has a lot of difficulties. It's very complex, but it's what we have right now. There are three kinds of public keys in X509. That's RSA, DSI, and ECDSA. Yeah.
What about the phenomenon key exchange?
That's not a key. That's not a public key algorithm, but it's a key exchange. It's something different. We'll get to that later. Usually everyone uses RSA. There are some people who use ECDSA, but not much. And both DSA and ECDSA have severe problems if you use them with bad random numbers. And getting good random numbers is a hard problem. So I think maybe these algorithms shouldn't be used at all. Yeah, and then we have signatures. Like we have a CA signing the certificate of a server. And for a long time, they were made with MD5. Like we knew since 1996 that MD5 is bad, and since 2004 we knew that MD5 is really bad. But CAs continued to use it till 2008 when there was a talk on the Congress where someone could create a fake CA cert with attacking MD5. You should watch that talk. It's very interesting stuff. And then they stopped using MD5. But then there was one of the, I think it was the Flame virus, which used some code signing certificate where they also attacked MD5 in a yet unknown way. And today we have mostly SHA-1. SHA-1 we know is not so good. It will be broken in a few years. but it's still de facto standard. If you ask the CAs, they will tell things like, if we have Windows XP without Service Pack 3, then they don't support SHA-256.
30% of the message by yourself.
Hmm?
With tray 1, you can choose 30% of the message by yourself already.
Yeah, maybe later, okay? It's yeah. So yeah, SHA-1 is not really optimal, and we want to move to SHA-2 or maybe to SHA-3 in some years. Also, a problem is that the signatures are usually using PKCS1 version 1.5, which is the old way of doing RSA signatures, but it's still the way everyone does, and we have better ways to do it. One is RSA PSS. The problem here is the old standard is not really broken. It's just you can mess things up easier. So if you use PSS, it's much harder to do it wrong. I wrote my thesis on it, and yeah, you can read it if you want. I have download link later. Yeah, but what this shows is we are using, often we use substandard technology. Like we have better algorithms, but we don't use them for whatever reason. Yeah, and now if we're done with the certificate, we have our TLS connection. And there we have a lot of algorithms. And here's an example for how such algorithms are called. What we have here is a key exchange with elliptic curves. We have RSA certificate. We have AES encryption with 256 bits. We have Galois counter mode, and we have SHA-384. And we have a lot of these algorithms. And as I said earlier, we also have a lot of algorithms that are really obscure and really aren't used at all. So I think we can clean up a lot here. Yeah, now we come back to the CBC problems I already mentioned earlier. Until TLS 1.0, AES CBC used something it's called an implicit initialization vector, which is it uses the last block of the previous encryption to initialize AES. It's quite a complicated attack, but this led to the Beast attack, which got a lot of headlines. But basically, this was it was known long before that this is a problem, but Beast only showed it's a practical problem. And it was fixed in TLS 1.1, but nobody implements better protocols if they don't have to. So it took this attack really to bring people. So at that point, everyone was using the old TLS 1.0 standard. And we have a second problem with CBC, and that is it uses, when we do encryption in TLS, we want really two things. We want that the message is encrypted so nobody can read it, and we also want it authenticated so nobody can change it. Like even if it's encrypted, it's bad if someone can like flip some bits or something. So we need two things. We need to make sure it's secret, and we need to make sure the message is it's not being changed. And TLS uses a combination. It first does a HMAC, which guarantees that it's not changed. Then it does some padding, and then it encrypts the whole thing. Now the problem here is originally TLS sent two error messages depending if you send a wrong package, like if you change some bits. And one error if the padding is wrong, and one error if the MAC is wrong. Yeah, this led to the so-called padding oracle attack. And then the kind of somewhat solution was we only have one error message, so nobody knows which error happened. And here is, somebody asked earlier if they knew that there's a problem. Here's the TLS 1.2 standard, and I have marked the important parts. This leaves a small timing channel, but it's not believed to be large enough to be exploited. So basically what they said was, we know there's a problem, but we don't care, or we don't think it's a real problem. Somebody has to show us, and this happened some years later. There was the Lucky 13 attack, which did exactly this. They measured the timing, they sent lots and lots of packages, and by the timing difference, they could repeat this old padding oracle attack with timing. And yeah. So, for all these CBC problems, we have workarounds. For Beast, we can do some splitting of the packages, and for Lucky 13, we can make the implementation constant time so timing doesn't happen. But after Lucky 13, many people said, okay, this CBC stuff is really, it's strange and we don't want it anymore. So they used something else, which was RC4, because it was the only thing that was left when you take CBC away. At some point, the PCI verification, which is for credit cards. So if you have a web shop and use credit card payment, you have to do this verification. You get checked by some company if your SSL is good and if your other things are good on your server. And they required you to use only RC4. Yeah, and then some people looked at RC4 a bit more closely. RC4 is from 1994. It was developed by Ron Rivest, which is one of the inventors of public key crypto. He didn't want to publish it. It was only for internal use, but it was somehow leaked into a news group. It's very simple. It's only a few lines of code. And very special thing is the code is in Wikipedia and you can just copy it. So it's very easy to use. And then in March 2013, Bernstein and others showed there's an attack on RC4 in TLS. It is a very impractical attack. You need to monitor gigabytes of traffic with the same data, but it was an attack that was doable on TLS, and there are no workarounds because originally we thought RC4 had some kind of, it's not really random at the beginning, so we just throw 100 bytes away and then it's good again. But this attack showed that that doesn't help. There are problems in RC4 no matter how you implement it. And then there was the Snowden revelations about that the NSA can break a lot of encryptions, and then some people said maybe the NSA can break RC4 in real time. There's no proof for that. It's just speculation. But basically the thing is, a lot of people think RC4 is bad. A lot of people think that more results will happen, that it will be broken faster sometime. So today, pretty much everyone thinks it has to go away. And there's a draft, which is written by Microsoft. So sometimes Microsoft does something good, which says that RC4 should be just forbidden in TLS. And yeah, I hope it will be finished soon. So basically with TLS, until 1.1, we have two options. It's RC4 or CBC with Mac then encrypt. Both are bad. CBC is not so bad because we have workarounds. It's not nice, but works kind of. What I have to say, all these attacks are not practical. They are like gigabytes of data and you usually need some kind of other cross-site crypting attack or something. But it's still not good. I mean, we want this is the most important crypto protocol, so we want it to be really secure, like no matter what, yeah. And the only way out at the moment is AES GCM, which is an authenticated encryption mode. That means the two steps like encrypting and making sure that nobody changes the message happen in one step. And it's only in TLS 1.2 and only very new browsers support it. And there's also a draft to just change the order of MAC and encrypt. And if you do encrypt then MAC with CBC, then it's safe again and it's completely fine. And so if this extension gets published, then you can use CBC again and it's secure again. And there's also a draft for quite a new cipher, which is called Cha-Cha-20. It's also a stream cipher, and it has been selected by some competition, the eStream competition, and it's really fast. It's faster than AES if you don't have hardware acceleration, and it's also faster than RC4. And a lot of people think it's really, really secure. It's also developed by Dan Bernstein. Yeah, so, and currently Google is trying to push this into the standard, so I hope this will happen and would be a good thing. Yeah.
I heard about a cipher also from Bernstein called Salsa. Is this still relevant?
It's, yeah, Salsa 20 is basically the same, just Chacha is, there were some results against Salsa, like theoretical attacks, and so he made some slight changes to improve it, and this is Chacha 20. Yeah, and it's probably even more secure than AES. Although I have no problems with AES, it's probably fine. Yeah. Then what else? Then forward secrecy. Forward secrecy is a great idea. You should do it, but you should do it right. What forward secrecy does is if we do some kind of key exchange with Diffie-Hellman or elliptic curve Diffie-Hellman, that means that the key we use for our communication never gets sent through the line, not even encrypted. So if later someone steals our private key, he cannot decrypt what we did before if he listened to it. It's basically, we should do this everywhere, like in all protocols. But in TLS, we have some problems. First problem is Apache. Apache, up until very recently, only supported Diffie-Hellman with 1024 bits, which is not enough. It's not secure, and we knew this since more than 10 years. And we can really expect the NSA is able to break this. So currently a lot of people have implemented forward secrecy, and they have implemented it in a bad way. Yeah?
You could use mod GNU TLS for key exchanges with larger Diffie-Hellman parameters already, but nobody usually uses mod GNU TLS.
Yeah, okay. He said that you could use GNU TLS and you could do this earlier, but now Apache, the latest versions of Apache also do it with OpenSSL. I mean, I don't want to debate whether GNU TLS or OpenSSL is better. Don't know. And the other problem is Java also doesn't support larger Diffie-Hellman exchange. With Java 1.8, they have changed it, but now they only support 2048 and not 4096, which is bad. Yeah.
The issue was why only 1024 bits was supported by Apache.
Apache had the parameters hard-coded, so they just had one parameter set, and it really was something. I mean, you have to think that before these Snowden revelations, many people didn't care that much about crypto. So it was just, there was a bug open and there was a patch and nobody cared. Yeah?
The arithmetic is roughly quadratic with the length of the key in words. So on 32-bit CPUs, longer key exchanges are very expensive. And when this code was introduced on then recent CPUs, it took like 4 seconds for a handshake.
Yeah.
And without session caching, this is completely unusable.
Yeah. Okay, I can repeat this. So basically, Diffie-Hellman is not very fast. It is a significant performance issue also. But still, you don't want to introduce forward secrecy and make it less secure. That's really not what you want to do. And now we have an alternative that's Diffie-Hellman with elliptic curves. So what about that? The idea is Diffie-Hellman and also DSA and Al-Gamal use some group. A group is something, a math structure. You don't have to know the details, but it's something where you can do some kind of operation on numbers, and it has to have some properties. And you could use any group you like. There are a lot of groups in math, and one group you can also use is elliptic curves. And the idea is with elliptic curves, it's much more secure. The reason is the best attacks on the discrete logarithm problem, which is the basis of the security of these algorithms, it doesn't work if you use elliptic curves. There are infinitely many elliptic curves. You could use everyone, so we have to choose some good elliptic curves. How do we choose them? It's quite obvious. We ask some organization that has a lot of experience with cryptography, like the NSA. I mean, they have a lot of skilled cryptographers, so they should know what elliptic curves are good. In 1999, the NIST published a standard for elliptic curves, and it was written by someone from the NSA. There's a slight problem with this standard, and it introduces some numbers that are not explained. This is one of these numbers. And what they do is they put this number into a hash algorithm, and then they say this hash algorithm obfuscates it, and so we haven't chosen any bad curve. The problem here is maybe they know some kind of 1 in a million curves, they have some kind of backdoor, and they try it as long so they have a bad curve. This is, I have to say, this is not very likely. So most people think these curves are not backdoored. But it's something we cannot really exclude. I mean, if they have a backdoor in there, then they really knew something. Nobody has an idea how it worked. But it gives you a bad feeling. Like, if we have something better, then we maybe should use something better.
Other plausible reason why you would publish those numbers without any explanation?
I don't know. I have asked them and they didn't answer me. You can see it like that, but it's really, if this is some kind, I mean, maybe they were random numbers and they just don't answer because they don't answer to people asking stupid questions. But it's really, it's unexplained, but it's, yeah, I mean, the cryptographers are divided over this. Some people think it could be, some people say it's almost impossible to have some backdoor like this, but it's some uncertainty. Yeah, other question?
Has someone tried to ask some researchers
Oh, what?
the university researchers?
I have talked to Tanja Lange, which is one of the leading experts on elliptic curves, and she said, like, yeah, she also doesn't know, but she brought this issue up. She was one of the people bringing this issue up. And she said, like, yeah, she will have a look at it and try to find something, but she doesn't expect to find something. So it's really, researchers say, we don't know, but we're not sure. Yeah?
Also, DJB and Nadia Henninger published their works on safecurves.crypto,
Yeah.
which gives a good overview about nothing of just leave numbers and stuff.
Yeah. I'll come to that right now. There's a curve that was developed by Dan Bernstein, which is curve 25519. I think Dan Bernstein might needs better names for his algorithms because nobody can remember that. But from the crypto, it's probably very good. Everybody I know thinks so. Everybody in the crypto community thinks this is really state-of-the-art elliptic curve. There's a draft to use this in TLS. It first would be only for key exchanges and not for public keys, because there we would need another algorithm, because ECDSA doesn't work with this kind of curve. But there's another algorithm, it's called ED25519, which is for this curve. And there's also the Safe Curves project, which lists a lot of elliptic curves and gives arguments which ones are good and which ones are not so good. I mean, they come to the conclusion that their own curves are the best, so maybe you should question that. But really, these are the leading experts on this topic, so maybe this is, at least you should listen what they have to say. Yeah. Then we have a problem with compression. TLS compression is also an example for feature bloat, I think. Some researchers found out that the compression leaks some information about the content, and they also had some kind of attack, which was also an impractical attack with gigabytes of data, but it was an attack. The recommendation was just disable it because browsers won't use it anyway. So we should have maybe disabled it from the start, because if it's not used, we don't need to enable it. Problem here is the similar attack works on HTTP compression, which is like a layer, which is on another layer. And it's very difficult to have workarounds for this. You can work around this in your web application with some modifications to the tokens for cross-site request forgery protection. But it's something the web app has to be aware of, and that's really something that many people haven't thought before, that compression might introduce security issues. And I think there's also more research will be happening on that. Yeah, some more problems, downgrades. Downgrades, that's a very ugly thing. TLS itself has a downgrade protection, but browsers have a workaround for this protection. What they do is, if they send a I want to make a connection with TLS 1.2 and the server says, I don't support this, then the server should say, okay, no, I don't support this. I only support older TLS 1.0. But some servers say nothing. If you say, I want to connect with TLS 1.2, then they just don't answer. So what browsers are doing is, if first connection doesn't succeed, they try with a lower protocol, and then they try with a lower protocol. Obvious problem, we lose all the security from the better protocols. And it's a big problem that we have a lot of broken hardware, broken routers, broken load balancers, all kinds of stuff. And also these downgrades, yeah, question?
Martin Breslin once wrote a post on Google Plus to disable in Firefox low secure fibers like RC4 also. And the problem was Firefox obviously choose first the low secure protocol, and when you disable it, it tried a higher secure.
But that's probably outdated. At the moment, it tries TLS 1.2. The problem is many servers don't support TLS 1.2, so you cannot disable the old protocols completely.
You could set about config and the key disable for that.
Yeah, you can disable it, but then you cannot access a lot of web servers. I mean, and this is like 2/3 of the internet. If you use only TLS 1.2, which is the only version which is really secure.
The problem is it tried from lowest common
It-
denominator upward.
No, it doesn't do that in the current version. Maybe in earlier versions, but definitely not in the current version. But we can talk about it later. And, yeah. Another problem here is that these downgrades also can happen by accident because you have a bad internet connection. Then it also disables all kinds of features. Like if it downgrades to SSL version 3, there are no extensions. And that means, for example, SNI doesn't work. SNI means you have different certificates on one IP, which is very important in web hosting environments where you have lots of web pages on one server. My recommendation, SSL version 3 should be disabled everywhere, in browsers, in servers. If you run servers, disable it. If your browser supports to disable it, then disable it. And if a server doesn't support TLS 1.0, then tell them they are stupid. When I first tried this, the Pirate Party website didn't work anymore, but they fixed it now. Yeah. One of the devices that had such problems was a big IP from a company called F5. They build a lot of enterprise internet equipment. And they also have a device that, with some firmware version, has problems if the TLS handshake is between 256 and 512 bytes. So if it's lower, it's okay, and if it's bigger, it's okay. So now we have a TLS padding extension to add some data so we don't fall into this area of handshake size. But there's other hardware that breaks if we have this extension. So, yeah. Browsers really do all kinds of weird workarounds for broken stuff. And now we now also have a draft for a TLS extension to re-enable downgrade protection. So now we have a workaround for broken stuff. I don't know if this is really the best way to go forward, but that's how things are at the moment.
Maybe sometimes it would be better to drive it against the wall.
Yeah,
Fix the real problem.
yeah, fix the real problem. But the thing is, the browser vendors say we cannot break too many stuff because then people will move away from our browser, don't like us anymore.
Just make all the browsers.
Make other browsers do it, yeah, then but you know,
There are just 3 relevant browsers these days.
yeah,
If 2 of them get together,
yeah, tell them I support you.
I can display this big annoying message. call your sysadmin. Tell him he's an idiot. You have to fix this, this, and this.
Yeah,
They are
May-
doing this with SSL certificates.
yeah.
They are doing this with SSL certificates with the big annoying messages.
Can we please move the discussion to the end? I want to get through the talk. So then there was an interesting research project on certificates, which was called Frankencerts. What they did was they took just some thousands of certificates from the internet, like real certificates in the wild, and then they changed some things in it. And then they checked what SSL libraries think about these changed certificates. And basically what should happen is all of them say the same, because either a certificate is valid or it's not valid. But in real world, it's not that simple. And they found lots and lots of bugs in the libraries. And they had found 2 very severe bugs in Matrix SSL and GNU TLS, and lots of minor bugs in other libraries. Then dual EC DRBG. This is this famous random number generator where we are almost sure that it has a backdoor by the NSA. Someone wants to disagree. Maybe we can have this in the discussion.
This is random. It's randomness.
Yeah, okay. There was a research project. They changed the parameters so they had the backdoor parameters, and tried if they can attack something with that. And it had a number of interesting results. One was that DSA and ECDSA, they could break the private key. So for me, this is again an argument. These algorithms are probably not very good and we shouldn't use them. RSA B-safe, this was known before. It used dual EC by default for some time, and they got $10 million from the NSA for doing that. Who knows why? I don't know. And they found that there was an extension proposed for TLS, which was never published as a standard, but it was just a draft called extended random. And they said it doesn't really make sense what they're doing here, but it makes this attack easier. So we don't really know what's happened here. And one of the authors of the extension was from the NSA.
If it was implemented in OpenSSL.
Was it implemented in OpenSSL?
Yeah, but didn't work. And nobody,
No.
nobody found that
No.
it didn't work.
No, this was the random number generator itself. The random number generator was implemented in OpenSSL, but didn't work because nobody used it. This extension was implemented in RSA B-safe, but disabled, and it's not open source, so they had to change the binary code, but they managed to enable it and try this attack. And yeah, what we can learn here is don't implement extensions if you don't really know why and what they should do. But we already know that from Heartbleed, I think. This dual EC random number generator is not really used on real world servers or software, so it's not a real problem, but it's very interesting research because it can tell you something about backdoored standards. Yeah. Then we recently had a paper, it was called the triple handshake attack, which was a bug in the logic of SSL handshakes and renegotiations. What they did was, it was only an attack on client certificates, and that's not used very often, so it's not a big problem. What they basically did was the server connected to a client with a certificate and could then use this connection to connect to another server with the client certificate of the client. There's a workaround in browsers. Adam Langley, which is a Google developer on Chrome, he has a check in his blog, so you can test if your browser has this workaround. What was interesting was that one way to attack this was by using a connection with very bad Diffie-Hellman parameters. And then I did some tests with this and other people also. One was that if you use very low Diffie-Hellman parameters, Chrome just crashes. It's fixed now, but yeah, and the browser, not just the tab, the whole browser crashes. And this Diffie-Hellman, one parameter is a large prime. Now, what's a large prime? 17, it's a prime, yeah. Some browsers accepted this, or 15, it's not a prime, but they also accepted it. No, 2 doesn't work. It needs odd numbers. No, no.
2 is the oldest prime.
Yeah, 2 is prime, but they reject even numbers. So everything that's divided by 2 is rejected. But I think 15 was the lowest where I got it to work. Yeah. The conclusion there was that we need to fix those parameters. We should just say in the standard, this is our prime, it's large and it's standard prime, and then you don't have these problems, because it's really crazy to say like you can use any kind of parameter. And also this is something I want to propose that you can do. Just try crypto algorithms with weird parameters and look what happens. Can really lead to interesting conclusions. Yeah, another problem we have, SSL stripping attacks. It's a very simple idea. You just intercept the traffic and you redirect all HTTPS links and or forwards to HTTP. This was invented by Moxie Marlinspike. He's also currently developing text secure. Maybe you know that. One idea to prevent that is HSTS, which is the first time you access a website via HTTPS, the browser remembers that this is a HTTPS only website. So the browser is forbidden to access it via HTTP. And also some browsers then have some built-in lists of web pages that should never be accessed by HTTP. And a warning here, if you have any kind of web application that does some hybrid solution with we only protect the login and later we move back to HTTP, this is insecure. It's insecure all the time. You cannot make this secure. Doesn't work. Yeah, then one thing you may know, these here below certificates or keys with these it's a base 64 encoding. ASN1, which is used in TLS and X509 all the time. It's really the most horrible format you can think of. It's a binary format and it's really, really weird. Just look how they save things. You don't want to write a parser for it. Just one thing, there's no piece of software to edit these things properly. At least I don't know one. If someone knows one, tell me. I'd be interested. So, and this thing has been out for like 30 years. I once had a problem when I was working with the code of NSS. Something with the ASN1 parser wasn't working. And then I was discussing this with other NSS developers, and then the bottom line was there are lots of workarounds for this bug in the ASN1 parser, but nobody wants to fix this bug because nobody wants to touch this code.
Maybe we should compile the ASN1 specification to a parser. There are ASN1 compilers out there. Some of them are even partly verified for space applications by either, and operate in constant memory with bounded buffers.
Yeah, maybe. But I really think it's not the kind of format you want to use. We can discuss this later. Yeah. Then quantum computers. This is really some years ago. People told me when I talked about quantum computers, this is so difficult, it will never happen, and if it happens, it will be many, many decades. The problem is quantum computers will kill all public key crypto we have today in real-world applications. It will kill all key exchange, everything we have in TLS, and everything we have in PGP, and everything we have in SSH will be broken. In 2012, there was a Nobel Prize for research where the Nobel Prize committee said this research could help build a quantum computer. So at least the Nobel Prize committee thinks quantum computers may be possible. And I heard people saying like maybe in 10 years, which is really not a lot of time to develop better crypto. There are some algorithms that are resistant to quantum computers, but it's very experimental stuff. And I think research needs to happen on this because if quantum computers become reality, we need something to switch to. And at the moment, we don't have anything really usable. One note about quantum cryptography, which is a different thing than quantum computers, it's the idea that you use some optical effects, some physical effects to make a secure key transport. Some people, I often read like quantum cryptography will save us from quantum computers, but this is basically total bullshit. The idea here is that you send single particles from one end to the other. Now, how should that work? We would need some kind of direct physical connection where we can send a single particle from one computer to another through the internet. This is basically not really doable in the real world. And there are quantum cryptography devices you can buy today, but they are not really secure because they don't send single particles, they send more than one particle, and then it's not secure anymore. And also, you need an authenticated channel for quantum cryptography, and it doesn't give you this authenticated channel, so you need this from somewhere else. So it's really not something you want to use. Yeah.
What about symmetric encryption and quantum computing?
Symmetric encryption will mostly stay safe. You can use quantum computers to reduce the attack time, but you can just compensate by using larger keys. Also, hash algorithms are also safe. You can attack them, but using larger hash algorithms, you are safe. So symmetric encryption and hash algorithms are not really threatened by quantum computers. Yeah, some very practical tips for server administrators. Use the latest Apache versions because of this Diffie-Hellman problems, because of OCSP stapling, which kind of may fix revocation. Because you want TLS 1.2 and you want GCM and all the fancy stuff. You probably want to disable RC4, you want to disable TLS compression, and you probably also should disable SSL version 3, then you won't have these downgrade problems and your SNA won't be broken. And also think about disabling all strange and unused and insecure algorithms. Export and null ciphers are disabled by Apache by default, but for example, seed or IDEA, I don't know, depends on how you configure it. Better look that they are disabled. Enable OCSP stapling because this one day might reintroduce working revocation, and use RSA certificates with 2048 bits at least, but today you won't get any smaller certificates from certificate authorities, and try to find the certificate authority that uses SHA-256. Some do now. And last tip, use the SSL test from Qualys. It's a very good online tool where you can just input your URL and it will tell you a lot of things about your SSL configuration, and you can learn really a lot just by reading what this says. And yeah. And it will give you some rating how good your configuration is. Yeah, question?
Shameless plug, I'm doing a talk on bettercrypto.org this night on 2115 in the workshop area, which covers exactly this.
Okay, he says bettercrypto.org, which is a project how to configure your SSL server stuff, will have a workshop later today. Yeah. Yeah, Firefox and Chrome support it. They will use it, yeah. Firefox has some bugs in it which recently caused problems for me, but they use it in theory. Yeah, with soft fail semantics, because the idea is that later you will add something to the certificate that you must have OCSP stapling, but that's not there yet. SHA-256 does not make any problems with current users. If you have someone who has Windows XP and who hasn't installed any updates, then you have a problem. But then you have more problems. I don't know any other problems. if you know some, you can tell me. But this will happen because Microsoft said sometime, I think 2016, they will disable SHA-1 support. So people have to move now. Yeah.
SHA-2 is limited to SHA-256 only. If you try to use SHA-512, which
Yeah.
is also in the SHA-2
GNU
standard,
TLS doesn't
you
support.
have a problem with GNU TLS 2.12. The GNU TLS 3 version supports it, but isn't in Debian and others.
Yeah, yeah, okay, I will repeat. If you use SHA-512, you may have problems with GNU TLS, some versions, and especially in Debian. Yeah. But SHA-256 is mostly okay. Now, I leave you with two possible conclusions. Conclusion number one would be this thing is so horribly broken. Just get rid of it. Make something new, something better. There are some people set up a web page where they said exactly this, and they want to discuss making something completely new. And yesterday there was a very interesting talk. They were even more radical. They said we need to get rid of the whole internet, how it's working today, and build something new. I think they have some arguments on their side, yeah, but I really don't believe in it. The other conclusion would be, yeah, we have lots of problems on many layers, but we also have lots of ideas how to fix them. And we have fixes in the pipeline, like there are drafts, and many of these drafts will become reality soon. So we just need to make sure that this stuff gets deployed. I let you choose your own conclusion, but I want to ask you, help making it happen. If you think TLS is so bad that you cannot repair it, then you should think, what can we do that the alternative happens? If you think we should repair TLS, then you can think, what can we do? And there's lots of things you can do. You can improve the software. You can just try to find out things, like make experiments, try to play around with the specification, try what happens if I do something completely weird, like, I don't know, use an RSA key with 10 bits or something, and maybe this breaks something, I don't know, would be interesting. Or try to help with, in the TLS working group, take part in the discussion, yeah. Or just read more and learn more about this stuff. I often write articles on Golem, and also for some newspapers sometimes. Very interesting is the blog of Matthew Green. He's a cryptographer in the US, and he's one of the people who knows how to explain this stuff that you understand it. Adam Langley, he's a developer at Google, and he's really one of the people who can write good crypto code and develop good crypto code, and also has very interesting articles sometimes. Dan Bernstein is a very famous cryptographer, also has a blog now. And there's a very good online course. If you really want to dig deep into crypto and want to start, then this may be for you. It's like a university course, but videos online. You can either just watch the videos, or you can subscribe to this course and then make some exercises, and then at the end you will get a nice certificate you can print out. Maybe even your university will accept it. You can try that. I don't know. Yeah, I have lots of sources. I won't go through them, but you can download the slides later and get the links. And I want to have some final words. Thank you, Edward Snowden, because since the Snowden revelations, this stuff is really discussed in another way and people are more aware. Yeah, thanks. And if nobody wants to throw us out, we can have some more questions or discussion. No questions? Yes.
So, until recently, I thought nobody was crazy enough to touch the OpenSSL code until some OpenBSD developers sacrificed their last sanity and reformatted the code into kernel normal form, making it readable for human beings, not just compilers. And yeah, their efforts are showing incredible crap, because there are things hidden in this code you wouldn't think possible before reading it. I took a short look into it, and found a function starting with some initial parameter checking. But before this parameter checking, there was a if0 block, if null, then a label, and some switch block contained a backward go to into the if0 block, which would then run through this code again. And
Yeah.
you
I mean,
want to read it.
the basic problem is these SSL libraries are really old, and they have grown over the years, and yeah. So it's also a legitimate question: do you want to fix them or do you want to rewrite them? But I don't know.
There's one problem with fixing OpenSSL, which will break a lot of things, because it's used in many small devices. Machine-to-machine communication is often neglected, which is very important as well in the industry. And if you just throw out support for a certain platform, it may be Cray or it may be Linux or something.
But I don't know if you anyway.
Half an industry because they can't update anymore.
I don't know if Cray is really that important anymore. But yeah.
You can
Well, it's a nice furniture.
A more practical question. I have really never heard about any problems with IIS. Does this mean in this particular case that Microsoft did a better job and that it's rather advisable to switch to IIS? Is the crypto implementation better in IIS?
So the question was if the Microsoft IIS crypto implementation is better. I don't really, I don't have a good answer to that. I don't know any famous attacks, but maybe it's not looked at so often because it's not used so often. But I really don't know. But I usually say in crypto especially, I would only use free software. I mean, I know a lot of people after OpenSSL said maybe this concept doesn't work as good, but I still think we need to have a way to look at the source. Just think if there's a backdoor hidden somewhere, and you can maybe find it by disassembling, but yeah. I think there are people who want to come in for the next talk, so yeah. Well,
Again about this. I'm a bit surprised that you showed it so on the other hand, you so easily dismiss the possibility of these spectral, maybe random numbers where we don't know.
I didn't dismiss the backdoor. I said it's hard to believe because it would be really, they would know something, we have no idea what it is. But
Wouldn't it be, especially, we thought a lot of things to be unlikely, now they turn out to be.
yeah.
Wouldn't it be more plausible to consider, well, it is the backdoor?
Well, one argument about that, we have this other backdoor and it's pretty obvious. So the question is, do they really have like the easy backdoors and the much more advanced backdoors? I don't know, but we can discuss this maybe later. But it's I mean, the bottom line is I have no idea how the math of elliptic curves work. I'm mainly repeating here what people tell me who I know they know the math. So, but I mean, I say stay on the safe side, don't use that stuff. Then we are sure that, then if there is a backdoor, better be on the safe side. So, yeah.
But actually, elliptic curves are some good
Elliptic curves are faster. If they are more secure,
if you look at quantum computers, they're good, aren't
yeah.
they?
Yeah, for quantum computers, maybe elliptic curves are more vulnerable because they have shorter keys. But there are some attacks on classic algorithms that are like very far away from real attacks, but that some people think could be a problem and are no problem for elliptic curves. So this debate, which is better, the classic algorithms or elliptic curves, is tricky, and there are arguments on both sides.
One good starting point is also understanding of what e.g. OpenSSL is doing internally. And I once read a blog entry where someone digged into the printf function of the libc and went down all the layers until the kernel core actually was done. client when you connect to a server and retrieve a web page from there. It's quite interesting. I'm on 30 pages and I'm still only to the start of the S client with the subroutine.
Yeah. I mean, look at the OpenSSL code. Try to find bugs. I mean, this OpenBSD thing. Maybe they will find something like Heartbleed in the next few days. I don't know. It's possible. I have to go now because I'm also having a lightning talk. Yeah, but I'd love to discuss further in private discussions. Yeah, just ask me or write me email.